This video is on exponential functions, and it's more of an introductory video to the basic form that exponential functions have and some of their properties and features. Along with, we will go over some of the limit notation that is used also more in a pre-calculus class. So our general form of an exponential function is going to look like f of x is equal to a times b to the x. So these values are going to play an important role because if you recall, when x is 0, in this case, we're going to have a non-zero number raised to the 0 power, and we know that is going to be equal to 1. So if we let x be 0, then this term becomes 1, and therefore you get a. So we say that a is going to be called the initial value, which happens when x is 0. And in this scenario, b is always going to be a positive number and not equal to 1 for an exponential function. So there are two scenarios that can happen depending on the value of b. So we're only going to play with this for right now. And in both of them, we're just going to assume a is positive. So because if it's negative, then that brings in a transformation. So we're not going to talk about that in this video. So assuming a is positive, then there's two scenarios that can happen for b, which would be called exponential growth, or we can also have a scenario where it's called exponential decay. And that is going to depend on the value of b. So if it's greater than 1, we're going to have a growing exponential. And of course, it could grow steeper or, less steep, depending on what that value of a is. And if b is going to be in between 0 and 1. So it's some number less than 1, but of course it always has to be positive, as we said above. Then you're going to have a decaying function or a decreasing function. And it can decrease, faster or slower, but it's going to take on that general shape. But in both cases, we should notice what you see, and that is they both have that initial value right there when x is 0, which is your y-intercept. So they both will cross through that value. Now, they also have what's called a horizontal asymptote feature, which means as the function is getting closer to 0, either on either end, it's actually not ever going to get there. It's just going to approach it, as we say. So that's kind of summarized here, that both graphs will have a horizontal asymptote, and we call that y equals 0, which of course is just the x-axis. So that can change with some transformations, but we're really just talking about the basic form in this video. Now, the domain of any exponential function is going to be all real numbers. So any value of x is free in this function. However, the range, as you can see above, in general, they're going to sit above the x-axis. So they're not ever actually going to get to 0. So we're not going to include it. It's going to just be a parenthesis. And so it's going to sit up here. So the smallest value would be 0, and then it's going to go to infinity on the y-axis. Now, they're either going to be always increasing or they're going to always decrease. So your growth is always increasing, your decay is always decreasing. So they won't change from one to the other. And in addition, they're either going to be always concave up or the other, always concave down. So both of these scenarios are always concave up. But as we said, with other transformations on it, it could also reflect and be the other way. And so then it would be always concave down. So we're not going to have any extrema and we're not going to have any points of inflection. Okay, so those are just some basic features. Now, just to get more acquainted with those, I have some practice for us. So there's a few things we're going to look at for each problem. So broken down into A through E parts. We want to look at each function and we want to be able to identify very quickly whether or not it's exponential growth or decay. We want to sketch the general shape. So we don't really have to plot points, but we do want to get the, label the y-intercept. Is it increasing or decreasing? Is it concave up or concave down? And then this one, we're going to bring in the limit notation just to help for a lot of the pre-calculus classes are kind of focusing on this as well. So let's go ahead and answer these questions. And we'll start with the first problem. Problem number 1 says, is it growth or decay? And so once again, what are we looking at? We're going to look at that value right there. So that is B. So if we want to just make a note, the A that we've been talking about would be 3, and the B would be 0.7. So that means that the initial value is going to be 3, but if B is 0.7, we know that that is going to be a value that's in between 0 and 1. And if you refer to up above, we said that's going to be a scenario where you have decay. So if we go to sketch that graph in just a very general form, we would put some point here, we'll just mark that as 0, 3, and then decay is going to approach here, and it's going to look like that. So that's a general form. We didn't plot any extra points, although you certainly can. And like we said, this is a horizontal asymptote, so I'm just going to indicate that with a dotted line, and we can label that there. So we have decay, which means it's always decreasing. And when we talk about it decreasing, it's always decreasing on its domain, which we said is all real numbers. And this one is going to be concave up. And limit notation for this one is going to look like, we're going to say what happens as x approaches positive infinity, which means you're going out to the right. And then we want to look at what happens as x approaches negative infinity as you're going out to the left. So we essentially want to fill in, we'll just say these blanks. So what is the function doing? So going to positive infinity on the x-axis means you're traveling this way. And going to negative infinity means you're traveling this way. So we're interested to see what the function is actually doing. Well, you can see as you go to the left, the function values are increasing infinitely. They're getting higher and higher and higher. So what we're going to do is say that this is approaching positive infinity. However, on the other end, as you go out to the right, you can see the tail is coming this way. And so as we described, it's approaching 0, the horizontal asymptote, and it's not ever going to go below there. So we're going to put here that the limit as x approaches positive infinity is going to be 0. Now we can do the same things for problem number 2. You still have, once again, you can see that your A value is 3. B is 8/9. So everything essentially is going to be the same as we had over here. Nothing else will really change because you still are going to have decay, because 8/9 is between 0 and 1, which means it's going to be decreasing concave up. And so your limit statements, your limiting behavior is going to look the same. So we can say that all of this over here works for problem number 2. And similarly, if you go down to number 3, the same thing will also work. because here we have A is 5/4 and B is 1/6. Now, these A values, see, these ones are both 3, but this A value is 5/4. So it would change definitely the way that it's decreasing. But so if we plotted more points, you would see a difference there. But the general shape for all of these is going to look like this. And because B is between 0 and 1, these are all going to be the same thing. So we would say for this one, all of it still looks like that. Okay, so if you wanted to see the difference between like what the A value is doing, it's just affecting the steepness. So, it could be just decreasing faster, or it could be decreasing slower depending on that A value. Okay, so you could play like in a Desmos and change the A values and see how that affects the steepness of the graph. But let's look at the last one, and this one is the one that's going to be a little bit different because here the B value is actually greater than 1. Okay, so all of these 8/9, 1/6, 0.7, those are all numbers that are less than 1. Okay, so this is the only example that's going to actually change the answer to those questions. So let's do this one. We're going to say here that A is going to be 0.2. So that's your initial value or your y-intercept. B is 1.6 and 1.6 is greater than 1. So we know now we can say this is exponential growth, which means that it's going to always be increasing. And in all of these examples, our graphs are going to remain concave up. So if we go to do a sketch, we'll just put some point here. That's going to represent our initial value, where A is 0.2. So we'll just call this 0, 0.2. And it's going to be growing, so it's going to look something like this. And we will also put in that horizontal asymptote. That's at y equals 0. And so you get a very similar graph, except for now this one is increasing instead of decreasing. Still concave up, still has these features that we talked about up there, but now the limit behavior will be different. They're going to switch. So if we have the limit as x approaches infinity of f of x, and then the limit as x approaches negative infinity of f of x. Now we're interested in seeing what is happening as you go left and right. And this time as you go left, you can see that you're now having the function approach 0. So this one going left is 0, but this one going to the right, as you go to the right, the function values are getting larger. So we say that's going to positive infinity. So the limit statements will look different in these cases, and growth or decay will look different. So you just want to get familiar with those as a start, and then there's more things that you can do with this, but this is just an intro video to making sure that you understand exponential functions, their general form, and basic features.